Sami, can you hear me?
Right. Can I start?
So, well, thanks everyone for being here. I'm very excited that Netflix actually interests that many people. Initially, when I proposed it, I was not sure how many people would be interested in the section from the Netflix. Um, it's been a lot of work and it's been fun to organize the session. I think the most difficult part was to reject that many talks because we received a lot of abstracts for this very small section. But we're lucky to have two invited speakers today. The first one is Sami Solanki. He unfortunately could not make it today because he has a balloon launch in Sweden that got delayed. So right now he's in Germany, but he's going to go his talk remotely, so it's very late for him. So without ado, Sami, you can go ahead.
Okay, I hope you can hear me properly. Thank you very much for this very kind invitation. It's a pleasure to tell you something about the sun as a resolved magnetic star. Before I do that, why is it not moving now? Yeah. Before I do that, I'd like to extend my sincere apologies for not being present there in person. I really would have loved to be. I was really looking forward to that. And this is the culprit, as you can see on the picture. This is the Sunrise Observatory. It's a stratospheric balloon-borne telescope and instruments, largest solar telescope ever to leave the ground. But unfortunately, it hasn't left the ground this season. It's still there. And the conditions have been reasonably atrocious, so that it's been a very, very frustrating 3-4 weeks now. But we are not given up yet. We are hoping it can still be launched in this season before the stratospheric winds break down. But that's not the topic of this talk, rather solar magnetic fields. So let me move on to that. What you're seeing here is a magnetogram of the sun taken by the HMI instrument on the Solar Dynamics Observatory. You all have seen magnetograms before, so I don't need to tell you that white means magnetic field coming towards us, black away from us. And you can see solar rotation here, etc. You can also see many different types of magnetic features on the sun. And let me just very, very briefly lead you through those. They're active regions. These are the largest bipolar structures that we have on the sun. One of these is pointed out here. There are a bunch of others on the disk. At this point in time, there is unipolar network. These are actually remains of all the active regions. When they decay, these individual polarities expand. And very often, these large unipolar network structures can then be the sort of the foot points of coronal holes where the fast solar wind leaves the sun. Besides this unipolar network, you often have what is called the quiet network or the normal quiet network or whatever it is called. That's more of a salt and pepper thing. Both magnetic polarities there, mixed polarity. Often the fields are a little bit on average. The average field over the whole region is a little bit weaker than in the unipolar network. Then sometimes polar fields are dealt with differently. They are actually not very different from the unipolar network, but they're at the poles, so they play a special role as far as the dynamo is concerned. At the time where this magnetogram was taken, it was close to activity maximum, so the polar fields were very weak. At minimum, they would be stronger. And last but not least, we have the so-called internetwork fields, which lie between the network elements, and you would actually not see very much of those. You see a little bit on these full disk magnetograms, even the really excellent ones returned by HMI, but you have to go to highest resolution to see them properly. And with on a previous flight of the same sunrise, which has kept me from coming to San Diego, we managed to get very high resolution observations of the internetwork. This is a magnetogram again on the right with white and black having the same meanings. There is a network element right down here in black, but almost everything or basically everything else you see is internetwork field. These are typically weaker magnetic elements with very little magnetic flux. I'll just be coming to them in the next slide. So let's start with active regions and say, what are active regions composed of? They're composed of sunspots. You see a very nice example here. There are more in this image as well. Then there are pores, which are smaller magnetic features, almost as strong fields, not quite as strong as sunspots, but minus the penumbra around the darker umbra. Then you have the plage or facular fields, which are composed of individually many tiny magnetic elements. You don't really see much of a white light signature or a continuum signature at disk center from these. At the limb, yes. In the cores of spectral lines, in the UV, yes, but not in the visible continuum. But they give a strong signal in the magnetogram. If you look at these different features, the sunspots have by far the largest magnetic flux, followed by the pores. You can see this on the bottom left of the slide. Pores are about 2 orders of magnitude less. The individual magnetic elements of plage, another order of magnitude below that, so that you have a whole bunch of different orders of magnitude there. Now, active regions are not the only thing that's present on the sun. We also have the quiet sun, which is composed of network fields, as I pointed out in the previous slide. The network is again composed of magnetic elements, which are not that terribly different from the ones composing the plage or the faculae. They have a similar amount of magnetic flux there may be a little bit less, but not very much. And then, of course, there are the internetwork fields, which on this magnetogram and image here are completely invisible. And the individual features, again, have about 1 to 2 orders of magnitude less magnetic flux. So that all in all, from the weakest elements that we have from the internetwork, which are at the current detection limit, right to the largest sunspots that we know, we're covering about 7 orders of magnitude of magnetic flux per magnetic feature. Okay. Now, another question we could ask is, how much magnetic flux is there in these different types of features? And maybe surprisingly or not, a single power law actually tells you the frequency, that is, how many magnetic features within a certain time frame, within a certain area, with a certain amount of magnetic flux appear at the solar surface. And it is proportional to the amount of flux, but inversely proportional with a power law index of around minus 2.7. So it's a very steep power law. And what it is telling us is that most of the magnetic flux appearing at the solar surface, almost all of it, by orders of magnitude, is in the form of the weakest magnetic elements, the ones with the least magnetic flux per magnetic. So the internetwork is totally dominating the amount of magnetic flux appearing at the surface. Sunspots, active regions, they're way down there. They're contributing very little to the fresh amount of magnetic flux appearing at the surface. Irrespective of whether it's activity minimum or maximum, this power law changes a bit, but the change is very small. It still remains far too steep, so that it is the small features which dominate. If, however, we then go and say, now let's not look at the amount of flux emerging at the surface, but let's just take an image. How much flux is there at the surface in the different types of magnetic features? We again get a power law, but one with a very different index. Here, this is much flatter, and it's below 2, or it's closer to 0 than minus 2. That means there is actually somewhat more flux in the larger features, in the sunspots, in the active regions, than in the internetwork fields. Very strange, no? And that's basically because the difference between them, it's almost, like you had taken minus 1, the difference. It's just because the larger features live much longer. And it's, in a way, consistent with the old Knevichev-Waldmeyer rule, which was put up for sunspots, which said that the lifetime of a sunspot is proportional to the maximum area that it has. Okay. After that, I'll jump to something totally different. When you go from the sun as a resolved star to a sun as a non-resolved star, what actually are you losing? And the first thing, and you all have heard this probably many more times than you ever wanted to, is that if you have, magnetic features with mixed polarities, opposite polarities within a certain spatial resolution element, this could be your whole star, but this could be a small part of the sun where you have unresolved magnetic features in there. By the way, this one here is a magnetic foot point, obviously. That you're going to get cancellation of your Stokes V signals, and Stokes V, the circular polarization, is the most sensitive to measuring magnetic field at the solar surface. Opposite polarities give opposite signs of Stokes V, and a lot of that gets killed unless you're in a very rapid rotator where the rotation velocities will separate them and you can start seeing some of the magnetic field again. But the sun is not a very rapid rotator, so what happens there? And we can play this game, we can take all the magnetic flux on the sun over the whole 360 degrees longitude, latitude from south to north pole, and we can take a signed average of that magnetic flux. And this is the signed average over a bunch of synoptic charts going, over something like 40 years. And you see it basically remains within around plus minus 1 Gauss. Many times it's much closer to 0 than that. That's not very different than the Earth's magnetic field, so not a lot. If, however, we take the unsigned average of the magnetic flux, or of the field strengths, then we get something which is more like 15 Gauss or so at the peak. And there is a caveat here, it could actually be a lot more than that. And if you compare these two, you'll see you only see about 5 to 7% of the magnetic flux present on the solar surface if you observe it as sun as a star, in an ideal case. Very likely, it's actually more like 1% or even less. And let me try and explain that in the next slide. That's got to do with hidden magnetic flux, a lot of it in the form of horizontal magnetic fields. The internetwork is full of magnetic fields. We heard that before. We saw that the vertical magnetic fields in the internetwork are not contributing that much magnetic flux, also because a lot of them are canceling out, but they also produce a lot of horizontal magnetic fields, which we can measure. And those suggest that there's something like 50 to 100 Gauss additional field in the internetwork that is missed. Most of the time, no full disk magnetogram is ever going to show you that. Most of that is just going to be missed completely. There are some observations that say that the predictions from simulations of small-scale dynamos, small-scale turbulent dynamos, and the movie running up here at the moment is from Matthias Rempel, one of his simulations on that. They agree with a wide variety of data. So although there is no absolute proof, there's still some more tests to be done. I'm relatively confident, also because as soon as you have a sufficiently advanced MHD code, you get these small-scale dynamos running. They're also expected on other main sequence stars and probably also non-main sequence stars. People around Benavir Bhatia, Veronika Witzke, etc., have been doing such computations and showing how they act on different stars. For example, they're much stronger, much more turbulent on earlier type stars and not that strong and active on later type stars. Okay. All right, so what I've been telling you so far, I guess you all have heard, maybe more times than you would have wanted, but this is here a new result. Cancellation of magnetic polarities. You need opposite polarities for that. But what about you have a unipolar region? And what you can do, you can take an MHD simulation, which we are seeing turn out to be pretty good. One starting out with a purely unipolar field, so almost all the magnetic fluxes in one direction. There are a few bipolar regions turning up, but it's basically unipolar field. I would have, if you'd asked me a year ago and say, okay, you reduce the resolution of this thing what will you see? I think you get exactly the same amount of magnetic flux. The answer is you don't. If you average the Stokes profiles from here, and it's a complex thing that's going on, these are strongly nonlinear effects, you actually see at the most half of the magnetic flux. If you average enough, you reduce your resolution too much, it's probably even less than half that you're seeing. For the sun, this might be a breakthrough. This might really resolve a long-standing problem, the so-called open flux problem, which says that the magnetic flux that you're measuring in the heliosphere in situ with spacecraft, outside the magnetosphere of the Earth, is about 2 to 3 times larger than the magnetic flux you measure on the sun's surface, and open flux in coronal holes. And so this could resolve that. On the other hand, it also means that even the large-scale fields you obtain from Zeeman Doppler imaging, etc., are likely underestimated by at least a factor of 2. Okay, there are other effects also, like, for example, sunspots. Is this going to play a role? I don't know. I'm not followed the literature of ZDI so much in recent years, but if you look at these 2 sunspots on the left, near the limb, they actually are, one is positive polarity, the other is negative polarity. But here, if you look at them in the magnetogram, each of them has 2 polarities. I will let these movies run, going from one end of the sun to the other. And now you can see that the 2 spots have different polarities. And now wait till there's only 1 spot surviving to the other side. And at the end, you see it's just showing 2 polarities again. That's because your magnetic field is expanding. That's shown here on the right in your spacecraft. It's not the spacecraft that's moving around the sun. If you want, it's the sun that's rotating, although it is the spacecraft also moving around the sun. And it's seeing the sunspot from different directions. And so you are typically seeing both polarities, field lines pointing to you and away from you. I don't know how big an effect this will be, if this is actually going to change things when you do Zeeman Doppler imaging. I'm not aware of people having taken this into account, but forgive me if you have done so or you know about that. As I said, my knowledge of the field is not that deep, but it's so striking in magnetograms that I just wanted to point this out. One last point. One really big advantage of having a resolved star is that you can use these resolved observations to test MHD simulations. And if you look at the image on the upper left of the sunspot, it's actually 2 images. One side is a simulation, the other side is an observation, and they look really similar, don't they? This is telling us that the simulations are in pretty good shape. And what that means is after we have tested them on the sun, validated them, we can use them to compute such features also on other stars where we cannot resolve them with the observations. And you can learn all kinds of new things. There is a nice poster by Tanavir Bhatia on this, where he shows his star spot simulations, also his stellar plage simulations. I'm just showing one thing is that the Evershed flow, the outward flow, the radial outward flow from sunspots, which is very strong in sunspots, gets weak on star spots on K-stars, and becomes very strange with a lot of inflows and outflows mixed when you go to an M-star. Okay. Conclusions? No, I've run over time, so I'm not going to show you these, but I do want to show you one last thing, which I'm not sure you will believe it, but believe me, this is definite proof for the existence of non-magnetic sunspots. You've heard of non-magnetic star spots, non-magnetic sunspots. This is really a first. You don't believe me? Well, look. Thank you.
Thanks a lot, Sami. Questions, and I will be walking around with this mic because otherwise he cannot hear you.
Sorry? Yes.
The microphone, because otherwise we cannot hear you. So, question. Well, I know who you are, but I have a question related to the comment about.
Sorry, I cannot understand at all.
Sorry.
That mic it's difficult.
No.
It's difficult.
Okay.
Can you write in the, no, you're not in the thing. Yeah, sorry.
Can you hear me better now? Sami?
This is a bit better, yes.
Oh, okay. So you just tell me your question. I can repeat this.
Sorry, it's very faint. Excuse me, forgive me.
The effects of the how do you guys think we should go for
No, also this mic is, it's doubling things. I cannot understand you really.
that is a technical difficulty.
Yeah, the mic up on the dais, that worked well.
Okay. Can you hear at all, or is it just for
Can you say it again on the dais? Just the mic on the dais. In the beginning, when we were setting up, it worked really well, but not with this mic.
All right. We're just gonna go. Can you hear me now?
Now, this is perfect. Thank you.
Cool. Go ahead and repeat it just into the
Yes,
computer.
okay, so the question was, how do you think we should correct for the reinterpretation of the ZDI field, right?
Well, we haven't actually checked, right? So what we have done is, okay, let me try and go back. You're talking about this effect?
Yes.
Yes, okay. So this is what we see for the sun. And we have only looked up to a certain spatial resolution, which is 6 by 6 megameters, which is quite small actually, because that was the size of the simulation boxes we had. It's, I guess, for a G2 star, this is, and they're two different independent groups that find pretty much the same thing. So I guess that's robust. How it will change for other stellar types, I don't know. This is something we really would need to study still, because it depends very much on things like Zeeman saturation, thermal weakening of the line, etc. And that depends on the spectral type.
Okay. Well, thanks a lot. Other very quick question, if there is one. Otherwise, we're just going to move on because we're on a very tight schedule and the technical difficulties are making it slower. Okay.
Sure. Thank you very much.
Thanks a lot,
Bye-bye.
Sami.
Is that what? Okay. Is that working on the mic? I think so, yeah. Okay, fine. So I'm Adam Finley. I'm a postdoc at CA Paris Leclerc. I'm working with Sasha Brum as part of the Wholesome ERC project. And I'd like to talk today about some results we just published. Is there a clicker? Or... Perfect. Thank you. Some results we just published, so you can go and check out the paper. I can also make the slides available.